Hey Phys 1 kids, Campbell here. In our next video, we're going to talk about solving problems using the law of conservation of energy. So I just want to go back to where I ended the last video on the generalized work energy principle. So this uses energy transformations and energy transfers all in one thing. So it's a great equation because it covers everything. It covers all our bases. It says that the initial energy, all the different types that we have, plus work is equal to the final energy plus any change in thermal energy. And so we're going to use this to solve problems that involve changes in energy. So let's talk about the steps. So here's an example of an elevator that's moving with a speed that's going to slow down over a distance. And in this case, I'd want to know what the tension force of the cable is. So the first step you want to do when you're solving any problem using energy is you want to choose an initial and final state. And in fact, the best thing to do is to sketch it. So I'm going to draw my elevator with the cable here. I'm going to put it above the earth some distance, and it says that it stops in 6 meters. So I'm going to choose the initial state. Actually, it's 6 meters above the ground. I like to call the ground zero all the time. And then my initial state, so it has some height then, it has some initial velocity, and then always set up a coordinate system in that drawing so that, because you have to have a reference for where is the gravitational potential energy zero, where is the height zero. And so that's why we want to include a coordinate system as well. And here's my final state. The final state is when the elevator is stopped, since I want to know what is the tension force exerted while stopping. So draw a picture, choose an initial state and a final state, because it'll help you answer the next question. Our next thing we do is we have to choose a system, because that'll help us with what energy is changing and what things are doing work. And so the first thing I like to do is when I look at my picture, what types of energy are changing? And I ask myself 3 questions. Is there height? Is there speed? Is there a spring? So obviously there's height, right? I have a height above the ground. So if I put the earth in my system, then I'm going to have a change in gravitational potential energy. I have speed, right? That's moving with the speed and it stops, which means I'm going to have a change in kinetic energy. There's no spring, so I don't have to worry about that. So my energy transformations that are occurring here, I have a change in kinetic energy, I have a change in gravitational potential energy, provided I put Earth into my system. Then ask yourself what objects are doing work. Well, obviously they want us to answer the tension force, which, yes, we could use kinematics and forces to solve for, but that's 2 steps, and this is 1 step. So that's why I like using energy if I can. Energy is a great thing because it's also a scalar, so I don't have to break things into X and Y components and do trig and all that stuff. So work energy is great. All right, sorry, I diverge. So from an external object doing work, that's going to be the tension, that tension force from the cable. So the cable is doing work to slow down the elevator. So there's my external force that does work. Now, if we didn't put the earth in the system, you can see I have this red box here that covers the elevator and it covers the earth. Those are my system. That way all those interactions are internal. So the force that the earth exerts on the elevator, right, the force of gravity, that becomes an internal force. And so that's why I can use the change in gravitational potential energy. Otherwise, if the earth was outside the system, we'd have work done by the force of gravity. So we're going to put it in the system. I like to put the earth in the system all the time because then changes in gravitational potential energy to me are easier than doing the force of gravity times distance, right, for work. And then we just set up our equation. Initial energy plus work equals final energy. So I have some initial gravitational potential energy. I have some initial kinetic energy, right? It's moving. And I have work being done by the cable. That's the tension force. So after that, ask yourself, do you have height? No, I don't have height, so I don't have any gravitational potential energy at the end. I'm at the ground where I set 0. Do I have any kinetic energy? No, I stopped, so I don't have any speed. Do I have any work being done by friction? Is there any friction going on? I don't see any friction forces. That means that my final energy is 0. So all the work being done by that tension force is going into taking all of the energy out of the system. We're transferring it all out. And now I could plug in, if we want to solve this, right, we do mgh plus 1/2 mv squared plus the tension force times the distance it travels, set that equal to 0, right? That's the equation we have right there, and solve for tension force. Let's talk about what to include in the system. You're probably like, why does she talk about putting the Earth in the system? So what you want to do when you choose a system is you want the biggest system possible. That way, everything going on is an energy transformation, and we don't have to worry about external forces. So that's why I say I always put Earth in the system, because then I can talk about changes in gravitational potential energy. Now, obviously, if you have information about forces like we did in that last problem, we wanted to find a tension force, then keep your force, keep that as work. Keep that as an external force. Don't put the cable and the motor into the system. Just keep it outside. And remember, like I said, in order to use gravitational potential energy, the Earth has to be part of the system. Otherwise, the Earth does work by the force of gravity. All right, let's take a look at some energy conversions. So let's talk about pushing a clay ball along a frictionless table by exerting a constant force. Notice I said the word force, so I'm thinking that we're going to have some work being done. So let's take a look at a picture, right? Sketch a picture, determine your initial and final state. So here's my picture. So I have a ball, I'm pushing it along a frictionless table by applying a constant force. Of course, it didn't say that it started off at rest, but obviously in my picture that's what I put. My initial state is just the ball at rest. My final state is the ball moving with speed v. Next, what are the energy changes? Well, clearly I have an energy change of kinetic energy, right? It starts at rest, so it has initial velocity of 0, and it has some speed at the end. So I'm having a change in kinetic energy. Do I have height? No, I don't have height, so there's no change in gravitational potential energy. Do I have a spring? No, I don't have a spring, so there's no spring force or elastic potential energy. The hand is doing work. We could have talked about that in terms of a chemical energy, right, that's being expended to allow the hand to push, but I don't know any, that's one thing you'll never get, is like the amount of chemical energy used. It's usually like there's a force, and so that means we have an external force, and that force is being provided by the hand. So when I set up the system in this case, I want to talk about it in terms of the hand does work to give the ball kinetic energy. So in this case, my system is just the ball. That way the hand is outside, and it's an energy transfer through work and not through energy transformation. When we set up our mathematical equation, right, where hand does positive work on the ball, here's actually an energy diagram, a graph of energy, which is a great way to visually look at what's happening. What we'd say is that work is equal to a change in kinetic energy, or by the generalized work energy theorem, we would say that the kinetic energy initial plus the work done by the hand is equal to the final kinetic energy. And so then we could break that down into 1/2 mass of ball, initial velocity of the ball squared, plus the force of the push times the distance. That's equal to 1/2 mass v final squared. So if I wanted to know what the velocity of the ball was after the push, this is how I could find it. What if that ball, we push that ball and it falls off the edge of a table? And we say it falls freely, that means it's not, there's no other forces that interacted on it besides my hand when I pushed it off the table. So again, let's decide the initial and final state by drawing a sketch first. So there's the ball. Its initial state is when it's on the table, moving with velocity, sorry, I don't know why it does this sometimes to me, moving with a velocity of v. The final state is it hits the ground where it's moving with some final velocity. All right, it hits the ground with velocity, then it comes to a stop. But we are just talking about it's falling down. What energy changes are going on? Well, if it's falling, right, I have gravitational potential energy, provided I put the Earth in the system, right? I have a change in height. So that would imply a change in gravitational potential energy, provided I put the Earth in the system. I have a change in kinetic energy, right? If something falls, it speeds up. So that means I have a change in kinetic energy. So do you have height? Do you have speed? Do you have a spring? I do not have a spring, so there's no elastic potential energy. External forces, if this is the case, if it's falling freely, there's no air resistance. And if I put the Earth in the system, then there are no external forces. If I didn't do this, so if instead, that's this case, if I said, okay, well, I don't want to put the Earth in the system, then I just have a change in kinetic energy, and the external force would be the force of the Earth on the ball, which is the force of gravity. In that case, I would. So here my system is the ball plus the Earth. And that's what I would choose because I like to deal with MGH rather than work, which is force times distance. Here, the system, in this case, the system would just be the ball. Our mathematical equation, if we go with this here, right, our initial energy, so we have initial gravitational potential energy, we have some initial kinetic energy, we have no work being done because I kept the Earth in the system, and that's equal to my final kinetic energy, because my my final gravitational potential energy, if I call like this height 0, then it would have 0 gravitational potential energy. If maybe it's falling farther, if I just wanted to know what it was like 2 meters above the Earth and it started at 20 meters, then I would have some final gravitational potential energy. So it depends upon where we set our height as 0. So in this case, I have no work, provided I leave the Earth out of the system. Now, if I did this, all right, if I use this instead, we would have initial kinetic energy. We'd have work done by the force of gravity, and that would equal a final kinetic energy. So we'd end up doing the same exact math. It's just a different way to look at it based off what we choose for our system. All right, last step here now, the ball lands on the floor and stops. All right, so initial final state, let's take a look at what that looks like, right? It was moving with some speed and boom, it stops on the ground. So my initial state is it lands on floor with speed v. And my final state here is it stops. Huh. Okay, so what energy is changing? Well, it had speed, right, before it stopped. So kinetic energy is definitely changing. If we look at our picture, right, it's landing on the ground and then it's stopping on the ground. So that means there's no change in gravitational potential energy. There's no height change. Huh. What other energy would change then? Where does the kinetic energy go? Well, my little bar graph came up, didn't it? The kinetic energy goes into, boom, thermal energy. It doesn't say, this problem statement doesn't say anything about force, right? We could talk about the change in kinetic energy in one case, and then work being done by the force of the floor. But if I don't know anything about that impact force, right, then I'd have a work is equal to change in kinetic energy. We could talk about the change in kinetic energy and the change in thermal energy, right? When something stops, where does the kinetic energy go? Well, it goes into the molecular motion of the molecules inside the object. So in this case, the molecules inside the ball are vibrating, and that's generating thermal energy, some heat, which is going to flow out. So let's take one more look at the system and environment stuff. We're going to do that by looking at a bike going up a hill. It is up to you what you choose for a system and environment, and it's really based off of the information you're given in a problem. If you're given information about forces, then whatever's providing that force you want to keep in the environment. Whatever energy transformations you have that you can calculate, the different types of energy we know how to calculate, we'd want to put those things in the system. So in this case, we're going to look at simple, and we're going to change our system so you can see how things change based off what you choose. In this case, if we start off with the simplest system, that means just the bike is in the system. And so in the environment, that means we have the person and we have the earth. So if we were to talk about the energy transfers in this case, we have a person doing positive work by pushing on the pedals. The earth is doing negative work, right? Because the force of gravity is down and the person is going up, at least on the way up. On the way down, it might be opposite. And those energy transfers are giving the bike kinetic energy. So if I wrote this as the generalized work energy equation, we'd say that the initial kinetic energy plus the work done by the person minus the work done by the force of gravity is equal to the final kinetic energy. So if we had information about those forces, this is the way I'd set up the problem. But we could expand the system. We could put the earth in the system. So now our system is the bike and the earth, and then the person's in the environment. If we do this, it allows us to make that force of gravity an internal force, which means now I don't have to talk about the work done by the force of gravity. Instead, I can talk about changes in gravitational potential energy. So in this case, with the bike and the earth in the system, that means that work is being done by the person pushing on the pedals to change the kinetic and gravitational potential energy of the system. So if I were to write this in terms of the generalized work energy theorem, I'd say the initial kinetic energy plus the initial gravitational potential energy plus the work done by the person is equal to the final gravitational potential energy plus the final kinetic energy. So if I had information about the force of push and the distance and the height and the masses, maybe some speed, this is how I would set up my system in my environment. But let's say we make the system really big, right? In the beginning, I said, make your system as big as possible. And so the biggest possible system we could have here is the bike, the earth, and the person all in the system. That means all of what's going on are energy transformations. There's no external forces because we put them all in our system. So in this case, that increase in kinetic and potential energy are actually coming from the chemical energy of the person that they're burning as they're pushing on those pedals. So now that's internal to the system. So our changes in chemical energy are actually going into changing our gravitational potential energy and our kinetic energy. So let's take a look at some problems. I'm going to have you actually do some of these problems on your own because this video is awfully long, but let's start off with one of them together. So Katie slides down a water slide. The starting point is 9 meters above the ground. She pushes off with an initial speed of 2 meters per second. The slide is frictionless. How fast will Katie be traveling at the bottom? Now you're probably like, oh, pushes, that's a force, right? Well, let's start as our initial state of right after the push. So I'm going to say that my initial state, and of course there's a sketch here already for you, right? I'm going to say that this is my initial state. It's after the push. The push did work, right, to get her going, which is why she has some initial velocity. And we want to know how fast she's going at the bottom. So it makes sense to choose this as our final state at the bottom. What type of energies are being transformed? What energies are changing? Well, gravitational potential energy, provided I put the earth in the system. I have kinetic energy changing. Do I have any thermal energy changing? Well, it says the slide is frictionless. So if it's frictionless, that's usually what generates our thermal energy. So nope, there's no change in thermal energy. So remember I said, ask yourself, do you have height, do you have speed, do you have spring? And then we should always look at internal energy or thermal energy. And in this case, I have height, I have speed, no spring. So changing gravitational potential energy, changing kinetic energy, that's what's being transformed. Is there work being done? Are there any external forces? Well, if it's frictionless, then the answer to that is no. So that means in my system, I'm going to put the girl, Katie, and the earth. We can put the hill in, the surface of the hill, but it's frictionless, so there's no work being done there. So we're just going to make this simple, girl and earth. So in our generalized work energy equation, that work part won't be there, but what it means is we have an initial gravitational potential energy plus our initial kinetic energy, and that has to be conserved, so that's equal to the final gravitational potential energy plus the final kinetic energy. All right, so that means that here we have mgh initial plus 1/2 mv initial squared, and that's equal to mgh final plus 1/2 mv final squared. When I look at this, right, we said that she's here down at the bottom, which is, if this is where we set the 0 point for height, right, then this term goes away, right? That's 0. And if we want to find out how fast she's traveling at the end, right, we can rearrange this equation, v final squared. I'm just going to divide everything by this, right? We're going to get mg, the initial height, plus 1/2 mv over 1/2 m. Why don't you just plug some numbers in and solve this, and I'll check your math in class because this video is getting awfully long. By yourself, let's see if you can solve these, and we'll go over them in class. So solve the problem in the next one on your page about Monica pulling her daughter. Notice this time I have information about the force. Her bike is pulling on the trailer with a constant force, so let's keep that out of the system. Let's have that do work. Look at your energy changes. So see if you can solve that for the speed at the top of the slope. And then finally, see if you can find the change in internal energy. So that's a thermal energy generated in this pole vaulting problem. See if you can figure this one out. This might be a little tricky. So we'll talk about it in class. So fill out your WSQ, and I will see you in class.